Our presentation today is a clear text explanation of the AES Cipher, and for your Shakespeare fans, does a Rijndael by any other name still smell as sweet? May 7th, blah, blah, blah. My name is Robert Stone. I represent Brainstorm Incubator, and I think with that, let's go ahead and get started. Let's start off with a little bit of an overview about what we're going to discuss today. We're going to start out first by discussing a little bit of the history of the Rijndael algorithm and AES itself. We'll cover first what is AES. We'll talk about the differences between Rijndael itself and AES. Also, there was a very famous recording made in a language other than English about the correct pronunciation of Rijndael, and they said it's fine however you pronounce it as long as you don't pronounce it DES. So, then we'll talk about how AES itself was selected. Great. Then we'll jump into the algorithm and implementation. Who knows what this machine is, by the way? Enigma, which has nothing to do with AES, but they don't make fancy AES machines, so you go with the images you have. We'll talk about the state. We'll talk about a bunch of these different steps that are involved, the different components of the algorithm, the sub-bytes, shift rows, mixed columns, multiplication in the Galios field modulo, and irreducible polynomial, which is always fun to say. We'll talk about the key expansion algorithm, the add round key step, and then we'll cover a little bit of the weaknesses in AES. So we're going to just very briefly touch on this. We'll talk about what side channel attacks are and how they can be a vulnerability, as well as related key attacks. Great. That being said, let's go ahead and jump right into it. First off, what is AES? AES stands for the Advanced Encryption Standard. It's a method of reversibly encrypting data. This is different from something like SHA or a hashing algorithm where you don't need to get the data back out. With AES, I need the data back out. I need to reversibly encrypt. This is what's called a block-based cipher. Block-based simply means that we're working with a fixed size collection of bits. It's significant because of all the operations we perform work on a block at a time. And there are certain ways you can stream data through it. We're not going to cover them too much here, but I do have a couple of references that talk about how you can chain data, how padding works, things like that. But for our purposes, we're just going to focus on the fact that it is a blockchain cipher. A block-based cipher with a fixed size collection of bits. AES is what's called a substitution permutation-based cipher. Might sound a little crazy, but we got a great example here. We have a little bit of plain text, Pearl Mongers. That's one of my local user groups. How many people are involved in their local user groups? Yay! Okay. Pearl Mongers, if you are a Perl developer, or even if you're not, and you're just interested in the language, I cannot strongly enough endorse getting involved in your local Pearl Mongers group. Mine's in Houston, so if anybody wants to come to Houston to visit, you're more than welcome. You can stay with me. I got an extra bedroom. But that being said, let's jump right into it. We have Pearl Mongers. The first step we're going to perform is what's called the substitution portion. Here I have just an alphabet, and I have a different series of letters that all map across. So the substitution step, if I look for P, P is going to get replaced by what letter? U. And that's exactly what happens. I have P to U, E goes to H, and so on and so forth. One interesting thing to note just in this particular substitution cipher is I do not have a substitution for space. That is actually a weakness of this cipher because it becomes very easy to predict. If I'm writing a sentence, most sentences start with the. And if I have a substitution cipher that starts with something, 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 space, you already have an inherent weakness. Fortunately, AES is much more complicated than this. But it works for telling us what a substitution cipher is. Next, we have the concept of permutation. A permutation is just a reordering, a shifting around of things. Here, we're just going to swap the U and the H. Come on. So, U and H swap, G and D swap, and we just continue that swap all the way down across the line. Together, this becomes substitution and permutation. Nice to see where that space moved. That's always fun. Great. So we have a little bit of a basic understanding of what substitution and permutation ciphers are. We're going to start now with a little bit of the history of Rijndael and how it relates to AES. Rijndael was created by two gentlemen, and forgive me if they're watching this. First of all, I'm flattered. Second of all, if I mispronounce their names, I'm so sorry. Vincent Rijmen and Joan Daemon. Rinjdael. Yay, it's a combination of their names. And it was not written by the NSA, interestingly enough, which we'll talk about other things that were at a great presentation tomorrow in this exact same room on pseudo-random number generators and the dual elliptic curve deterministic random bit generator. Yeah, you guys should come to that one too. Great looking guy is presenting it. AES is a form of Rinjdael with one primary restriction. And that restriction is that Rinjdael allows blocks and keys of 128, 160, 192, 224, or 256 bits. This is Rinjdael. But AES does not. AES only allows a subset of these. It allows 128-bit block. It must be 128-bit block. And a 128, 192, or 256-bit key. Other than that, Rinjdael is AES. It's the exact same algorithm, just with a couple of extra restrictions put on. Probably one of the main reasons they did this was to make it easier to implement. When you have too many options, how many people are like trying to do anything where you have 15 different command line options? I got to write a script and I don't know what I'm doing. Try to simplify it a little bit. Also makes it easier to prove from a mathematical standpoint behind some of the security aspects. Okay, how was AES selected? Why AES? Well, in September of 1997, the NIST, the National Institute for Standards and Technology, which we kind of trust, but we don't really trust them anymore, make up your own mind, they came out and they said DES stinks. The data encryption standard, it did us well for a long time, but we can see that computers are getting better, they're getting faster. We need something new. So they held in August of 1998 the first AES candidate conference. And at this conference, 15 algorithms were proposed as potential replacements for DES. From there, the second AES conference, March 1999, it was whittled down to 5 algorithms. After that, they had the third AES conference, April 2000, where they had some final discussions. And ultimately, in October of 2000, the NIST announced Rinjdael for the Advanced Encryption Standard. They selected the Rinjdael algorithm. So it took a little bit of time after that. In February 2001, the FIPS, as everybody calls it, the Federal Information Processing Standard, was published. This is basically the manual, the guidebook. This is what you need to know if you're an implementer. This is what you need to know if you're a cryptographer. This is how it works. So FIPS, people kind of call it the Bible of these sorts of encryption algorithms. Okay, so we talked a little bit about the history, who created it. Now let's get into the fun parts. Let's get into the actual algorithm and how it works. We start out with just the encrypt method. Okay, this is going to be combinations, pseudocode, real code, just kind of follow along with it. We start with input. The input has to be converted to the state. Now, a lot of these terms aren't going to make sense. That's fine. We're going to cover them in detail as we go through. But for right now, we're just going to do a general overview of them. Just checking my time. I'm looking good. Okay? Our input comes in. It becomes the state. Then we have our key, and we must expand the key. The key is very similar to what you would call a seed for a random number generator. Don't quote me on that because it's so not true. But from a very high level, the key is just the initial piece of data that you're going to use. A larger key has to be generated from that. Then we have the add round key step. This is where we basically add the round key to the state. Then we're going to perform a number of rounds. Depending on the number of bits in the key, it changes the number of rounds you do, between 10, 12, or 14. Most of the conversations we're going to have today are going to focus around 128-bit keys. It just makes it easier than having to have 5 times the number, well, I guess 3 times the number of slides to actually get across. Once we're in here, this circular operation, we have sub-bytes, shift rows, mix columns, add round key, and this will continue. We continue through this loop for each round. Then we have one more series of steps. We have a sub bytes, a shift rows, and the last add round key step. After the add round key, we now have a state that is cipher text. So we must convert that to actual output. So we have a state to output step. Okay? We're going to kind of be referring to this as we go as our guide. So everybody's memorized it, right? Great. The state. The state is where all the operations take place. It's the internal representation of a block. When we say that this is a block-based algorithm, this is the block. The state is where all your operations are performed. Input initially is just an array of bytes. It could be a string, it could be a credit card number, it could be anything. But ultimately, it's little more than a string of bytes. The state is composed of several parts. Just some terms first. We have the concept of a bit. I know everybody knows this already, but completeness sake. Bit is a 0 or a 1. A byte being 8 bits. A word being 4 bytes. And then we have the concept of columns and rows. Well, I'm just going to back up. We're going to do that one more time. Okay? This is our input. This is ultimately going to be our state. A column is of the size one word. Here is the one word that comprises this column. Okay? So we see how this translation occurs. We have the same concept for a row. A row is one word as well. And in this example, this is going to be our row. So this is how we map the input to the state. Again, all of our operations take place upon the state. So we need a way to map whatever information is coming in to the format we need to work with. So that's our background on the state. Okay? The first algorithm we're going to talk about, or the first step of the algorithm, is the sub-byte step. This is a substitution step. Just like we swapped P's for Q's or whatever letters they were. I probably should have known that. But whatever letter we had earlier in our Perlmonger's example, we have the substitution step of AES, the sub-bytes. This uses something called the S-box. We kind of made up previously our alphabet and then a second version of it. The S-box is that second version. We start with a byte. In this case, let's start with 53. And that's in hexadecimal, by the way. All these numbers are going to be in hexadecimal. We break it into its x and y components. Well, we have our x and we have our y. Then we look up the row on the x-axis. Great. And we look up the column on the y-axis. We have our 3. Excellent. Where the two intersect, is what we're going to substitute in. So in place of 53, we're going to replace that byte in the state with the indicated byte. In this case, ED, because that's what the S-box told us to do. Now there's also an inverse S-box, but yes.
But what's the purpose of the substitution? How would the algorithm be weaker if we didn't do the substitution?
That's an excellent question. I'd love to talk to you about it afterwards. I apologize. I'm just limited on time. So if we have some time at the end, we will.
Is the S-box always the same S-box, or is it based on your key?
The S-box is always the same. The S-box is a provided substitution framework. Okay. Okay? So we talked a little bit about the substitution step and the usage of the S-box. The S-box is provided. There's technically nothing that stops you from coming up with your own S-box, but nobody else's encryption would be able to work against you, and you would be unable to be certified by the NIST as, yes, this person implemented this algorithm correctly. Okay, and it's hundreds of thousands of dollars to do it, and you got to have all this crazy stuff go into it, so that you don't have to use it, but everybody uses it, which you'll find in tomorrow's presentation why that's not necessarily a good thing. Okay, let's talk about the shift rows. This is the permutation step. Just like how we swapped the ordering of 2 bytes, here we're going to act upon the state in a row-by-row fashion. We want to recall that a row is one word in size, which is made up of 4 bytes. Each row is left shifted here with carry. So here we have an example of the state. This first row has no shifts. The first row just gets carried over to our new version of the state. The second row is left shifted 1 byte. So we're going to left shift with carry. What's going to happen here? Where's this 27 going to go? Excellent. We'll do our 1 shift. So we have BF, B4, 41, 27. And that just comes on down. It becomes the next part of the state, or our updated state. The third row is left shifted 2 bytes. In this case, we have our first left shift and our second left shift, and ultimately we become our new part of the state. Again, it's the exact same thing. We're just moving over twice this time. Fourth row, left shifted 3 bytes. As you might imagine, we just do it 3 times to get our new makeup of the state. Okay? And this is the shift row step. Okay? A lot of what we're performing here is just to make it as challenging as possible to work backwards. So hard, though, or so challenging to work backwards that it's actually considered almost impossible. We'll talk about some of the weaknesses later, but we're trying to add as much diffusion to this as we can. Okay? So we just talked about shift rows. Let's cover mixed columns. Before we cover mixed columns, I want to introduce the concept of a finite field. A finite field is simply a field that has, I wonder if I could move this. Oh, I can. Excellent. It's simply a field that has a limited number of members. That's what makes it finite. It's a field of integers, in this case, that we can perform certain operations to. We can redefine things. We have the ability to redefine normal operations, addition, subtraction, if we wanted to, XOR, dot products, anything like that. But when we create a finite field, we have the ability to basically make our own rules. And the way that we work in the finite field, we must define it with an irreducible polynomial. The divisors of this irreducible polynomial are only 1 and itself. That's what makes it irreducible. Okay, if you could make it smaller, it wouldn't be irreducible, and it wouldn't work as well. And it's the modulus operation that keeps us in the field. If we weren't making use of modulus in our irreducible polynomials, we would not be able to constrain ourselves to the finite field. And if we didn't have a finite field, we would have an infinite field, and the math wouldn't work. We wouldn't be able to do things like redefine our own operations. Okay, mixed columns, this part gets a little hairy, so we'll kind of go through it nice and slow. We want to recall that the state is where all of our operations take place. And a column is 1 word in size, which is made up of 4 bytes. We have a little picture of the state. Excellent. Okay? For each column in the state, we're going to multiply by the columnar polynomial in the Gaussian field 2 to the 8th by 3x mod x4 plus 1. Wow. Surprising. There's not a lot of money in cryptography. You know, so much math and all that. Now, there is something special about this one polynomial. It's specially chosen because it has an inverse. And we need the inverse in order to decrypt the data. Okay? Okay, yeah, nice, but this doesn't really sound like anything I could actually implement in code, unless somebody has some library that does it for me. Fortunately, this is matrix multiplication. So, everybody remembers matrix multiplication, right? You do some magic and some things happen. Okay, great, fantastic. Oh. Fortunately, there is an even easier way. Okay, and easier is kind of mentioned here in quotation marks, because when you see it, it's not going to be that much easier. There actually is a formula for each byte. Okay? This looks to me like something I actually could implement. Does Boost have a library for matrix multiplication, maybe? Hopefully, somebody somewhere, CPAN? Okay? But this actually looks like something I could code in. Okay? In order to do this, for each column, we're going to look up the formula for the column byte. Okay? We'll perform the operations 1 part at a time. Okay? The multiplication that we've redefined in the Gaussian field 2 to the 8th, in this case, is going to be mod this equation. It's going to make sense why we use this equation in a moment. Okay? So this defines what this operation is. Here, we've defined this to just be the exclusive OR. Whew, finally, something I know. Exclusive OR, that we can do. Okay? Let's take a look at what this actually means. Because so far, it's just a bunch of cool words that are fun to say and, you know, big hit at parties. Beer pong, Gaussian field multiplication. Okay? The steps that we're going to follow are relatively straightforward. First, we have to convert the input bytes to polynomial notation. Now, the input bytes here are coming from the state. Okay, that's where all of this is coming from. Okay, this is from the column that we're working with. Okay, so we're going to convert the input bytes to polynomial notation. There's a really nice way to do this. It works out nicely. If we're working with 57 as our input bytes, okay, in binary 0, 1, 0, 1, 0, 1, 1, 1. Excellent. We can map this just to the exponents. So when we do this, we actually say, by performing this mapping, x to the 7th, we don't have that. But we do have an x to the 6th, an x to the 4th, 2nd, 1st, and 0. And any number to the 0 power is? 1. Great. So we have x to the 6th, 4th, 2nd, 1st, plus 1. Okay? So we have mapped our input bytes, 57, to its polynomial representation. This is something I can work with in a computer. I don't know what to do with that, with x's and things like that. But this I can perform operations on. And I can perform operations on it pretty quickly. If I need to shift it or XOR it or anything like that, I know a computer's very good at doing that.
So when it's raising it to the exponent, it's like ORing it, XORing it 7 times there, or 6 or 5?
It's more of a mapping than anything else. You're just kind of keeping that. It's an implementation detail. It allows you to map that way. We're going to perform the multiplication against something. In this case, 83. Here we have this representation in binary. In the end, what's our equation going to be?
X to the 7th, x to the 1st plus 1.
Yes, fantastic. X to the 7th plus x to the 1st plus 1. Okay, that's our first step. So we know what we're going to work with. Excellent. Second, we're going to multiply the polynomials. Again, this is looking like math I know how to do. X to the 6th times x to the 7th. It's kind of like FOIL, but there's more terms to it. And what we're going to do is we're just going to multiply out across because multiplication is distributive. Right, exactly. So we have x to the 6th times x to the 7th. When you're multiplying exponents, what do you have to do to them? Add them. So 7 and 6 is 13. And we just follow along. Okay? So we have this equation as our first part. Now we need to distribute the x to the first term. We have our result here, and my favorite one, distributing the 1, just is going to give us back this actual equation. Oh, I must have missed a click there somewhere. Okay, so this is the result of these multiplied polynomials. It's too much data to work with at this point. We need to simplify it. Okay, and the way we simplify is simply by performing an XOR operation based on the order of the x values. So we're just going to perform, this is from the previous equation, red, yellow, green, red, yellow, green. Okay? It's just the x representation written in binary. In order to simplify the polynomial, all we do is we go ahead and we exclusive OR everything down. Okay? So in a case where I have 2x to the 7th, that term drops off. I hope I don't have another one. Okay, good. We only have 2. So that term's going to drop off. When we do that, we end up with this polynomial in the end. X to the 13th plus x to the 11th plus x to the 9th, so on and so forth. Who sees a problem with this?
It doesn't fit into a byte.
Not only does it not fit into a byte, which is an excellent observation, it's not a member of our finite field. It's too large. This is going to get moduloed. And if anybody would have gotten that, I would have been so impressed. I would have probably handed you the presenter. But the problem is that this is too large. Okay, we're not in our finite field. We need to perform the modulo operation. So our next step is to modulo the simplified polynomial with the irreducible polynomial. Okay, I'm doing okay on time. Okay, so x to the 11th, blah, 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 blah. Modulo this. Surprisingly easy to perform. As long as you have, in Perl you do pack and unpack to get your ints and you're just working with large ints. Because you have this mapping so that you can actually turn this into an integer, you can just perform a regular modulo operation. Okay? The answer is x to the 7th plus x to the 6th plus 1. I think I made you guys suffer enough with some of the complex math, so just kind of trust me on that, hand wavy. Okay? X to the 7th plus x to the 6th plus 1 is the resultant polynomial. Okay. Let that digest for a second. Yes.
Weren't we modding out by x to the 4th plus 1, or how do we select it?
Because we've redefined in this operation.
You selected a different modulus to work in.
Correct.
And you checked that that's irreducible.
I personally did not check, but this is what's used by AES, so I'm assuming it's irreducible. I mean, that's a huge assumption, I will concede, but I feel fairly safe in that assumption.
And your coefficients look like they're in Xenon too. Your coefficients look like they're either 0 or 1. They don't move up to 288.
I do understand what you're saying, and I think that that's a fair statement to make. I typically do not think of the coefficients in this example and in this algorithm entirely because there's nowhere for me to store the coefficients. I don't care about coefficients. I only care about the orders, the powers, because that's how I can implement it.
Coefficients are 1 to 0.
I agree. That is likely the correct answer. But I don't want to tell you something and be like, yeah, that's how it works. And then someone's like, no. And I'm like, well, So that being said, that is an incredible amount of math that has to be performed. Okay? And even though a computer can do it, there's a much faster way to do this. All this math we just did, do I actually tell it to you on this slide or not yet? Yes. Okay. All this math we just did, you don't actually do in AES. You work out the answers to 2, 3, and I believe there's a 1 somewhere. Maybe it's an inverse. But you work out the answers to the first 3 Gaussian fields. You basically work out these solutions because there's only a maximum of FF in any column, or I'm sorry, in any byte. So you pre-compute these and you store them in lookup tables. It's much faster than trying to perform the actual operations. I did actually implement the operations to benchmark it because obviously it was going to be faster to do a lookup than anything else. And half for the actual implementation of it just to explore it. And I do show a link to where you can actually see that implementation. It is scary, but in reality, in real AES, it's important to understand how to do it. It's kind of like using a calculator. You're not allowed to use a calculator in school until you know how to perform the operation. As an undergrad, if I wanted to integrate, I had to do integration by parts or something like that. My favorite part about grad school in stochastic models was that I could write proof by TI-89. And as you kind of move on, you're allowed to use the lookup tables. Okay, so we talked about the mixed column step. Now we're going to cover the concept of key expansion. When we initially have our smaller key, 128 bits, it's not enough to let us perform all the rounds that we need to. So we must expand that key. Rather than having an input key that's 2,000 bits long or whatever the math works out to, you just kind of have this sort of initial key that gets expanded. This happens through the expand key. Yes?
So none of the previous steps were derived from the key? Substitution, the mixed column?
From what we've explained, no, because we haven't explained the add round key step. Okay. However, when you're really doing the operation, add round key is one of the first things that you do. But because I don't want to jump around too much, for what we've discussed so far does not use the key yet, no. Okay? We're going to talk about 128-bit key extension. Just for simplicity's sake, the only real difference is the number of rounds, and there's an extra step for 256-bit, which I will show you later, but we're going to constrain our discussion right now to 128-bit keys. First we have expand key is going to be equal to the key. So the first 128 bits are going to be the initial key. Then we're going to go through 44 rounds. Whew, a lot of rounds. Typically in implementation though, you don't do it one round at a time. You do it in groups of 4 because the operations that you only perform fancy operations on one word at a time. But what we're going to do is we're going to start with the last word. And the last word is the last word in the expanded key. Okay? If the round number, modulus 4, equals 0, then we kind of jump off. And we do a rot word step, a subword, and we XOR the last word with rconst. And we'll talk about rconst in a little bit. It's just simply round constants. But we'll talk about them in a little bit. From there, we take our prior word, which is 4 words ago in the expanded key, and XOR that with the last word. And in this case, this would be, you could think of it as like a temp we're actually operating on the last word as we do this. Okay? From there, we return the expanded key after we've completed all of our rounds, our 44 rounds. Okay? So ultimately, the entire purpose of key expansion is to build the expanded key from our initial key. Okay? Might sound a little complicated, but we're going to go through it in the same way that we went through sub-bytes and all that fun stuff. First operation we're going to talk about is raw word. Before I do this, I want to make sure this point is clear. We're only performing these operations on certain parts of the key. Okay, so for raw word, this is the permutation step. In this case, it's very similar to how shift rows works. However, in this case, it acts on a single word. As we're going through these rounds, we're always dealing with a word. Okay? Recall a row is one word in size, which is made up of 4 bytes. So we're talking about 4 bytes. In this case, the word is left shifted once with carry. So this is last word at this point. And we're going to left shift it once with carry. Simple enough. 19 comes to the end. Shift everything over. That's the raw word step. Just permutation. We're just rotating. The subword, from the name, I bet you guys can imagine what subword's going to be. Is it a permutation step? It's a substitution step. And it does make use of the S box again. It's very similar to sub-bytes. However, in this case, instead of acting on just one byte, it acts on all the bytes of a word. Again, we're using the S box. For each byte in the word, 19, 3D, E3, BE, I have it broken down in X and Y's. We look up the row on the x-axis, just like we did before. We have our 1, and then we look up the column on the y-axis, our 9, and that's going to give us our result by finding the intersection D4. So in this case, we replace the byte in the word with the indicated byte. Remember, we're trying to build the expanded key. We're going to be concatenating on to the key as we go. So we're still trying to build that. Our first value here is going to be D4. We repeat the process. 3, D, 27, so on and so forth. We have E3. And we have BE. Okay, so we've performed the subword operation. We've made our way through these. Having completed subword, now we can talk about XOR with the rconst. Rconst is just the round constant. Okay? We XOR the resultant word from subwords with the relevant value from rconst. Again, this does not happen for every single word. Okay? It happens depending on which round we're in. Rconst is just round constants. They are derived. There's actually an equation to get them. Okay, mod x, x to the I minus 1, so on and so forth. Okay, where I is the expansion round that we're currently running, because we're going to do up to 44 of them, divided by 4. Okay, so we get this equation, and we ultimately work out a solution like this. Nobody does this calculation. Okay, just like they don't for the Gaulius field math. They have this actually pre-calculated. Okay, so we have, these are the results of this equation for these values of I. Okay, you actually don't need all of them. We only need the first 14 values, because the largest you could have is 256-bit, which when you do the math to it works out to be 14 values of I that are necessary. So it's much easier to just have them in a hash or something of that nature where you could store them. Okay, what we're going to do in this step is we have our word that we're operating on. We have our rconst. We're going to XOR them. To make it a little easier, just kind of mask off the bits that I don't care too much about right now. 8a maps out to this in binary. 01 maps out to this in binary. We perform the exclusive OR operation, and we ultimately end up with our result. In this case, 8b is what changed here. Okay? And this is our XOR with rconst. Okay? Lastly, we have XOR with previous word. And I love this because it's just an XOR. Okay? Very similar to XOR with rconst. We extract a word, 4 words from the end of the key expansion. So we're basically going back. So we're at wherever we are right now, and we're going to go back 4 words, copy that out, and perform this operation. Our previous word, and I have this kind of represented using substring to kind of make it a little easier to understand. In this case, our previous word would be 2b, because I'm going all the way back. 2b, 7e, 15, 16. This is my previous word. Okay? I XOR with temp, or I'm sorry, I XOR temp. Temp is either going to be the last word, it'll either be this value, or it'll be the result of after we performed the other modification steps that we did. The subword, the XOR with rconst, so on and so forth. Okay? And this is where we get this from. So expansion round, depending on what it is and where we perform our modulus, basically where we are in the operations. I'm actually doing better than I thought I would. Okay. We'll have temp is equal to either the last word, which would be this, or the result of subword, rot word, last word, rconst, expansion round, blah, 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 blah. Fun stuff. Okay? We perform the XOR operation and ultimately end up with the new word. This new word is then concatenated onto the end. We have expanded the key by 1 word. And this operation repeats. It repeats until we hit the point at which we have derived sufficient amount of keyness for for the operations we're going to perform. Let's take one more look at key expansion, just the overview. We talked about how we end up with the expanded key in the end. We have our last word. Depending on where we are, we perform these additional operations, prior word, XOR, all this fun stuff, to eventually return the expanded key. We're constantly concatenating on to the end. Yes?
So let's say that I want to cipher some message and I have a passphrase that I want to be human memorable. So it's something like, my dog eats yellow, right? Now, how does that relate to the key? Is that considered the 128-bit key? Is there a step that...
The most direct answer I can give you is AES doesn't care that you want to have a memorable key. It's up to whomever the implementer is to perform some sort of mapping. Maybe they will hash your memorable phrase to generate a key. But AES doesn't allow that sort of thing. I have to have exactly 128, 192, or 256-bit key. Okay? I don't care that you want something less or more or something like that. Same thing with the block sizes. Okay? I don't care how big your message is that you want to encrypt or how small your message is. That's not my problem. Okay? That's the problem of whoever is trying to feed me that data. And that's where you get into the concept of padding or you chaining block cipher or electronic code book or anything like that.
Is there like a standard kind of way to do that so that if I, encrypted something in Java, I could decrypt it in Python?
As long as I have the same key, yeah. How you derived your memorable key, there isn't really a portable mapping. There's no official standard that says, all right, perform SHA-1 and on a phrase, and then that become. There isn't really something like that, which is why it's relatively rare, even though it should completely work. It's relatively rare for languages to decrypt each other's strings. Okay? It's certainly possible. You absolutely can encrypt something in JavaScript, and decrypt it. That's why this whole document exists. That's why this central method of doing this does, so that you can perform it. But typically, however you encrypted it is also going to be the way you decrypt it.
Okay.
Yes?
So you mentioned this comment to the key. Industry standard is using the key derivation function. So if my dog eats yellow isn't 128 bits in size, throw it through a key derivation function to produce one that is 128 bits in size, and then use that for your key.
There you go. Excellent. Let's keep moving forward. Okay, we have one more piece of the encryption algorithm that we want to cover. So we kind of detoured for a second. We talked about how keys are expanded. Now we're going to get back to the algorithm itself. We're going to talk about the add round key step. Here, all we're going to do is we're going to XOR each column of the state with a word from the key schedule. So here we have our state. Here we have our key schedule. Okay? We want to recall that a column is one word in size, which is made up of 4 bytes. So we have one column. For each column in the state, we're going to extract the column, which is going to be 1 word in size. Then we will go ahead and take, I'm pointing at this as if you guys can see this. we will take one word from our key, perform the exclusive OR operation, and ultimately find our result. This is our new values in the state. Okay, let's perform it one more time. Okay, we're going to take a column. In this case, the second column. Okay, or 1 if you want to count from 0, but we're not. It's the second column. We have this. This means we're then going to take the second word. In this case, this will be our value. We'll perform the exclusive OR operation, and we will generate our second column of our new resultant state. We'll repeat it again with the third column. No, thank you. With the third column, and then one more time with the fourth column. Okay? And all we're doing here is we're taking one word at a time and exclusive ORing them with every column from the state. Great. Ooh, come back. No, back. Okay. We just gone ahead and we went through the entire algorithm. Okay? It doesn't sound like it would be that bad, and frankly, it's not. Okay? Some of the math, when you're trying to understand the deep underneath how things work, can get a little hairy, but from an implementation standpoint, it's not too terrible. Okay? We talked about how the input becomes the state. We talked about how keys are expanded, how we can start with 128 bits and yet get enough bits to perform the encryption. We talked about how you can add the round key through exclusive OR operations. The sub-byte steps, shift row, mix columns, and add round key. We also covered a little bit about when it's okay to actually perform the underlying math, multiplication, the Gaussian field, modulo, and irreducible polynomial, and when you just have lookup tables, because somebody has already done the work for you. After we perform this sort of loop, then we have just 3 more steps. A sub-bytes, a shift row, and a final add round key. After all that has been completed, the state is now composed of our cipher text. And in the same way that we had to map input to the state, we then map the state back to output in the same way. Okay, let's go just briefly into some of the weaknesses that exist. Yes?
So just one. Does the initialization vector have something to do with AES, or is that one of those higher layers?
That initialization, that's actually a great question. The initialization vector is not related to AES. It's instead related to how you can chain information. Because it's very rare that I want to encrypt exactly one block. Okay? What you do instead is you use something like electronic codebook, which wouldn't use an initialization vector. But instead you would use some sort of chaining block cipher. And that initialization vector is what prevents the exact same plain text from generating the exact same cipher text.
Okay.
So yeah, that's actually a great question, which I talk about in my module, but so little time. Okay, let's talk just real quickly about side channel attacks. First off, we have the concept to define what is an attack. An attack is a methodology that gives you basically the answer, the result, in less time than brute force would. Anybody can brute force something, okay? But to call it an attack, it has to be better than brute force.
Much better.
Well, it doesn't have to be much better. It just has to be slightly better. It's technically an attack. It might not be a good one, but it's still an attack. We have certain characteristics of a side channel attack specifically. A side channel attack does not attack the algorithm itself. It's not a vulnerability or weakness in AES that side channel attacks attack. Instead, it targets the system or hardware that's running the algorithm. We want to think, what sort of information could a system leak? Okay? First, we have timing information. Okay? If you have access to some of this side channel data, you can, maybe it takes longer to calculate values that are larger than others. By having timing information, you're able to kind of peek in and take a view of the state and see what's going on underneath the hood. One of the pieces of information that can be leaked is timing. The next is power consumption. Surprisingly, certain operations require more actual wattage. Electromagnetic fields, this is that example of, all current is moving electrons. That's going to generate a magnetic field. If I could snoop into that, maybe I could see exactly what was going on there. Sound, surprisingly sound. Okay, how many people, well, I guess nowadays everybody has solid state drives. But when drives were working, you could hear them.
Also, your capacitors are going to fluctuate in sound based on what your power is doing.
Oh, excellent. I didn't know that. we have responses to bad input. Okay? This is where people will just throw bad information at it, just kind of see what happens. And lastly, we have the concept of data remnants. And this is where, you know, when they say with a hard drive, you have to completely destroy it, you know, like microwave and scratch, you know. If your data is valuable enough, you know, and the key on there is worth enough money to somebody, they could bust out the scanning electron microscope. I like bust out, like just carrying it around with them, you know. And they could try to get the underlying data. Again, these are weaknesses of basically any encryption algorithm. They're not limited to AES because they don't attack the algorithm itself. What there does exist in AES is what's called a related key attack. The circumstances for this are so outlandish for it to happen, but it is theoretically possible. And because of it, there are some consequences of this. A related key attack in AES exploits what's called the lack of diffusion in the key schedule during key expansion. In other words, the way that you generate the rest of the key from the rest of the key schedule from the initial key, it's not random enough. Random's the wrong word. It doesn't perform enough substitution, permutation. It doesn't mix things up enough. It's actually possible to track back to try to figure out what the actual underlying key was. We've seen this algorithm before. Okay, this is exactly what we were doing earlier. Okay, in this case, I did include what happens with 256. This is the expand key. This is the operations we're performing. Okay, just like we remember. What's interesting about the related key attack, though, is that AES does remain strong against all forms of the known related key attack. All known forms of related key attacks. The reason I want to show this to you one more time is to actually look at the scope. How bad is it, in other words? While the key attack does reduce the solution space, okay, it makes it better than having to brute force it, the actual computability is outrageous. Instead of having to brute force 256, it brings it down to 110 to 119, depending on which academic paper you're looking at. For 192-bit, 176, you know, a little bit. 128 actually turns out to be not vulnerable. Way beyond the scope of what we're discussing here. Okay? But what I want to make clear is nowadays they consider roughly 80 bits. And I mean if you got money. 80 bits is the maximum something you could actually brute force. And for this attack to work, you have to have several keys generated by the same person who share some sort of commonality. Maybe they use the same seed to generate them. You know, so the circumstances are pretty outrageous. However, because of this fact, there's a problem with AES. And the problem is that derivative ciphers that use AES can never be provably secure. You cannot turn this, or you cannot feed everything into a Turing machine and mathematically prove, you know, with a non-deterministic push-down automata or something like that, that AES is a secure algorithm. It is a weakness. Okay? Practically, does it make that much of a difference? Not really, at least not now. Maybe not for the foreseeable future, but someday this may actually become a problem. So maybe there will be another AES, and it'll be your it'll be your application. You know, that'd be great. I could say, you knew me when? Yes.
Just a comment. The size of 81 bits is twice the size of 80 bits, obviously. So when we're talking 110-bit security margin,
this is correct. This is correct. It's not only like double as hard when you increase numbers. It's orders and orders of magnitude. It's powers of 2. Okay. Yes.
So if the main problem is just the key expansion, how hard would it be just to refine that single step of the whole process?
You know, this is an excellent question. I wish I could give you a real educated answer on it. I would have to kind of defer to cryptographers. I imagine that that's a potential solution. It's something they could do.
Nothing else has changed.
But I mean, you know, I imagine if they were prepared to invest the type of energy and money to make those sorts of changes, they'd probably change other things too. That actually covers everything I wanted to. I just want to go through just a couple of references real quick. The NIST specification of AES. This is the FIPS document. It's FIPS 197. We have an additional full example where it works everything out bit by bit if you wanted to see it. I actually have implemented this in Perl. This is crypt Rinjdael pure Perl. You can see how I've performed every step, and if you look on GitHub, you can actually see when I used to do it using pmod and the Gallia field instead of doing actually just having it in memory and pulling it out. There is a paper regarding the related key attacks against AES. A lot of the math is pretty heavy in that, but it is interesting. Beyond that, any questions that we have left? I guess while we're letting our next speaker get kind of set up. Please.
So how is export law and all this stuff? You know what I mean? Like if you post it on GitHub, are people going to come after you because it is strong?
That's an excellent question. I'm not a lawyer, so I don't really know what the export law is.
President Clinton removed the cryptography export laws.
Oh, really?
Just before everybody starts going, I cannot thank you enough for coming to Openwest and coming to my presentation. It really means a lot. It's a full house. If anybody wants to get in contact with me later, I have some of my business cards just so call me late at night when you're having drinks, talk about cryptography, good times. But guys, thank you so much. It's such an honor to present for you. So thank you.